confirmation about the audio, please, guys. If the audio is clear and available, kindly confirm the same. Thank you. We shall be starting in a couple of moments. Vikram, the reason that you can ascribe to the shifting of the axial tilt is basically that planet is a kind of a spherical object. It is not a perfect sphere. It is slightly bulged around the region of equator. So imagine a sphere which is consistently rotating out there in space or in lack of air whatsoever. So the center of gravity in itself and the center of mass that keeps on changing with respect to time over a period of time as the planet rotates. For example, you would also have seen that, for example, if you would have in your childhood days, you would have seen a spinning top. Now that spinning top, if you rotate it, or any ball that you rotate, it is not always going to be rotating at the same place in the same way. It keeps on having some amount of tilt here and there. So that is how the planet's mass in itself is responsible for that shift. So after some time, the actual tilt basically after every around 26,000 years, the actual tilt increases to around 24 degrees. 24 degrees, and then when it tilts significantly, then the other bulge or the other side of it over a period of time pulls it back, takes it to somewhere around 21 degrees. So that kind of 21 to 24 degrees of shift is always there. Okay. So hello, a very warm good evening to all of you, and welcome to Baiju's Exam Prep IAS. Welcome to another session of geography, where here we shall be continuing our discussion where we left off yesterday. So yesterday we looked at some of the basic concepts about the origin of universe. We looked at the theory of expanding universe provided by Edwin Hubble. Then we looked into the portion of Big Bang theory which was provided by Lemaitre and Gamow, and what the concept of it was. Then we looked at planet Earth as a rotating and a revolving object, as planet Earth basically would move around the sun. Now it takes around 365 days to complete one a movement. And it is because of the actual tilt of the planet that different areas they get varying amount of exposure to solar rays. So as a result of that, you have certain months of the year where you will find that there is a greater duration of daytime in certain areas and greater duration of nighttime in certain parts of the year. So that variation in the length of the day and night is also created due to that axial tilt, which leads to the occurrence of various different seasons. We looked at the concept of latitudes and longitudes, how to number them. And now, today, we shall be initiating the discussion from international dateline. Moving ahead, we will be moving into the portion of geomorphology finally, where we shall be talking about the origin of planet Earth. How is it that planet Earth came into existence? We shall also be taking a look into the aspect of the interior structure of planet Earth. What is the interior composed of? What are our sources of information when it comes to the interior of planet Earth? And basic types of the rocks, basic information about the rock types that we have, that we find around us. And then we shall be proceeding ahead with some of the important theories of geomorphology, that is the continental drift theory, the convection current theory, the seafloor spreading theory, and how all these theories eventually helped us understand the theory of plate tectonics. So here, first of all, we initiate the discussion from international dateline. Now, what is the international date line? So again, it is a kind of an imaginary line which is demarcated, which ends up differentiating one day from the other, right? So, in order to understand that, for example, let's suppose we consider this to be the prime meridian, which passes through Greenwich near London. That is your prime meridian. Okay. Now, as I told you yesterday itself, that this prime meridian is used as a reference pointer in order to keep track of the time, and the time observed at that prime meridian is also referred to as the international standard time, or basically universal time, or the Greenwich mean time. So it is the reference time followed internationally. Now here, various different longitudinal extents rather, they help us understand what is the time experienced in different areas. For example, when we talk about India, Indian Standard Time. Now, Indian Standard Time is 5.5 hours ahead of the time observed in Greenwich. Why that is the case is because India lies to the east of Greenwich, or India lies to the east of London here, right? India is here, Greenwich is here. So obviously the sunrise will happen much earlier in the case of India, right? We will experience sunrise and sunset much earlier as compared to London, right? So Indian Standard Time overall, when you consider Indian Standard Time, it is Indian Standard Time is 5.5 hours ahead of GMT, or Greenwich Mean Time. Right, 5.5 hours ahead of GMT. Now here, when we say, let's suppose, what this actually means is, it is also represented as GMT plus 5.5 hours. So, if in India it is, let's suppose, 5 p.m. as of now, let's suppose it is 5 p.m. in India. So, what will be the time observed in Greenwich near London? What do you think? What will be the time observed in Greenwich in London? So for that, you have to subtract 5.5 hours, right? So it will be roughly around 11:30 a.m. Very good. So if in India it is 5 p.m., then in the region of Greenwich, it will be 11:30 a.m. Okay. So that is the case of the time zones which we generally observe. Now, if I take you to this particular image here, let's suppose here, if you notice, in this image, it is written +1, +2, +3, +4, +5. That means these are the regions which will experience sunrise first and earlier as compared to the region of London or Greenwich, because the planet continues to rotate in a direction of west to east. So obviously, as it rotates from west to east, this portion which is on the east will experience sunrise first, will experience sunset also. So as you can see, +10, +11, and so on. So if you are present in the eastern portion of Siberia, let's suppose. So this is indicating +12. That means GMT +12. So if it is, as we have seen, if in Greenwich right now, in Greenwich it is 11:30 a.m. So what will be the time in the region here in Siberia? If in Greenwich, if GMT right now, let's suppose, is 11:30 a.m. So what will be the time here? Very good. It is plus 12. So in this region, it will be 11:30 p.m. At night, 11:30 p.m. at night. That is the time which will be observed there. But if we go here on the other side, you observe -1, -2, -3, -4. So that means the sunrise is happening here after what you observe in the region of London. Right? Sunrise is happening after that. So around 180 degrees longitude, that is in the region of anti-meridian, you come across a scenario close to around 180-degree latitude, that is around the region of anti-meridian. You will observe -12, -11, -10. So here in Alaska, you observe the time GMT -11. This is your GMT -11. So what will be the time here right now? If at GMT it is 11:30 base AM, so what will be the time observed in Alaska as of now? -11 hours you have to do. Very good. It will be 12:30 AM. Here, 12:30 AM. So in Alaska, it is night time, but it is basically 12:30 AM of 14th of December, isn't it? So here, sunrise of 14th of December is still to happen, isn't it? So that is where the entire region will experience. Basically, we have almost done living with the 14th of December. We are done with the date of 14th of December, and tomorrow it will be 15th of December. But the region of US, the region of Alaska, basically right now it is night time there, and they will be waking up in the morning in a few hours. So basically, there, because the planet rotates on west to east continuously, you will have night time here also, but that will be the night of 11:30 p.m. of 14th of December here. 14th December, isn't it? Here it is early morning of 14th of December. So in half an hour, around half an hour to 1 hour, Siberia will be entering into 15th of December, because it is 11:30 p.m. there. So in half an hour, they will be entering into the new date, that is around 15th of December. But what about the region of US? US, after a few hours, will be experiencing its sunrise, and then it will be experiencing 14th of December. Then after that, after 24 hours, then they will be entering into the era of 15th of December, or the date of 15th of December. Right. So that is the case where you have around 180-degree latitude, longitude, that is what is referred to as the anti-meridian. Around the region of anti-meridian, you have that imaginary line which is referred to as the international date line, which differentiates one day from the next. That is your international date line. It is almost in the region of anti-meridian, but this is not a straight line like other longitudes. It is quite a zigzag line, as you can see. And that zigzag lineation is basically because of the fact that you have the case that, if let's suppose if this line would have been straight, let's suppose this line would have been straight, so it would have cut countries' borders into half. So the same country would have experienced two different dates simultaneously. So that obviously would not make sense. So in order to avoid the borders of the country, so that to ensure that a country at one particular time experiences only one particular date, that is where you will find that the ideal is quite zigzag here. Okay, so that is the case of IDL. Now, here, when we talk about the IDL, what happens if you cross the IDL from here to the other side or either side? That is something that we have to know about. So the dateline is not straight. Ideal is not straight, basically. So the dateline runs from North Pole to South Pole and marks the divide between the Western and the Eastern Hemisphere also. It is not straight but zigzags to avoid political and country borders. Okay. And it is so as to ensure that not to cut some countries in half. That is why the ideal is basically a zigzag line. Now, when we talk about the IDL, let's suppose we talk about the IDL here. Okay, a random rough image, let's suppose. Let's suppose this is your IDL. Now, this portion will be considered west of IDL. This portion will be considered east of IDL, international dateline. So, if let's suppose we are talking about the region of US, now United States is to the east of IDL. If we talk about, let's suppose, Japan, Japan is basically to the west of IDL, isn't it? So you have to the east and to the west of IDL. Now, here, let's suppose someone crosses from Japan to US or someone comes from US to Japan. What will be the adjustment that they have to make? For example, let's suppose in half an hour, we have seen that the region of Siberia, the region of Japan, will basically be experiencing 15th of December. Let's suppose you have your birthday on 14th of December, and here you have 14th, let's suppose, and here you have 13th. Okay, because here the next day is still about to come. So as the planet rotates, basically, this will also experience the new day. But let's suppose, as an individual, you are moving from the region, you have basically taken a flight. Let's suppose you have your birthday on 14th of December. You take a flight from the region of Japan and you fly into US, let's suppose. Now, in that case, what will happen? There, you will again come to encounter 14th of December. You will get to relive that day again. So, in a way, in your life, you are living that day again. Here also, you have celebrated your birthday, and after one day, you are moving into the other region. But maybe you have taken a flight, moved by a boat, or whatever. But then again, you get to experience that 14th of December. So, we can say that in your life, you have gained a day, isn't it? So, when you cross from west to east, when crossing from west to east, west to east, you gain a day. We can say that basically you end up gaining a day because you get to live 14th of December again. So, gain a day in your life. Now, how will you adjust? Let's suppose the in your watches you have your calendars or the date marker in your watches. Your watch is indicating 14th of December, and you have reached a region where it is still 13th of December, which is being celebrated. So, how will you adjust your watches there? What will you do? You basically will have to subtract a day in your clocks, in your calendars, everywhere. You have to subtract a day in order to adjust to that new area, isn't it? So in this case, we talk about subtract a day. But what if, let's suppose you are catching a flight from US and you are moving to Japan. In US, you were basically experiencing and celebrating 13th of December. By the time that you land in Japan, you find out that there it is 14th of December night. So basically, you have almost lost a day because that day basically you have lost it because there while you were in US the sunrise still had not happened, it was still 13th of December, and then you suddenly crossed over to US to Japan where 14th of December is almost over. So when you cross from east to west, crossing from east to west, east to west, You tend to lose a day. Okay, you tend to lose a day in your life. But how will you adjust your watches in that case? While you were basically experiencing and celebrating 13th of December there, now while you have reached Japan, you are experiencing and celebrating 14th of December. So you will have to add a day in your calendars, clocks, watches, everywhere. You have to add a day. So that is the adjustment that you do when you cross the international date line. Why do we have to adjust? You don't adjust, but basically when you reach that area, if your watches and the clocks, they indicate the previous date and that region is celebrating or experiencing a new day, you will have to basically shift that clock, isn't it? So that is the case of the adjustments that you make when you cross the ideal from either east or to the west. Now, those of you who have a doubt that US is to the west, Japan is to the east, now all of that is with reference to where? With reference to India? Ankush, you have that doubt. Japan is on the eastern side and US is on the west. With reference to what do you say that Japan is to the east and US is to the west? Direction is never absolute. Direction is always relative. For example, is India to the east or is India to the west? If I ask you this question, what will you write? That is India to the east or to the west? Let me know. India is to the. Now, again, I will have east also, west also. But when I say with reference or with respect to Japan, is India to the east or to the west? Can you say that India is to the east of Japan? No. India is to the west of Japan. But if you talk with respect to Pakistan, India is to the east of Pakistan, isn't it? So, direction is never absolute. Direction is always relative. So, when we are having the relative marker as international date line, so with that respect, US is considered to be the east and Japan is considered to be the west. If you consider, let's suppose, India, then you can say Japan is to the east and US is to the west. Okay, but that direction cannot be paramount and cannot be fixed for every place. I hope you are understanding that. Okay, so that is the case of ideal. So what happens when you cross the ideal? So when you cross the ideal from west to east, that is from the direction or from the region of west of ideal, this is your ideal, from the west to the east, you end up gaining a day in your life. And that is where basically when you gain a day, you have to subtract one day in your clocks and calendars. So that is where you subtract a day. And if you cross from east to west, vice versa, you tend to lose a day because the other region would have experienced sunrise at that point of time. The other region would have experienced the conditions of the next day also. So you have to add a day in your clocks and calendars. Okay, so that is basically the case of IDL and what happens when you crisscross the region of international date line. Now, this is a particular portion which is relevant for your prelims. What happens when you cross the IDL? Okay, now then we come to the various systems of planet Earth. So, when we talk about planet Earth, basically it is composed of various different, it is said to be composed of major systems which drive the features of the planet. For example, we have the lithosphere, hydrosphere, atmosphere, biosphere, and what is also known as cryosphere. What are these? So, lithosphere, the surface or the ground on which we stand, that is what is known as lithosphere. Okay, so lithosphere is the surface or the ground that we stand upon. Okay, I'll tell you the exact technical detail of lithosphere also when we talk about the interior structure of planet Earth. But the surface on which we are standing upon, that is your lithosphere. Hydrosphere, all the water bodies, the seas, and the oceans of the world, they end up dominating and forming what is known as hydrosphere. Then the blanket of air which surrounds the surface, which surrounds the planet, that is what is referred to as the atmosphere. Now, biosphere, all the living beings on the planet, all the living beings living on the planet, that is what is known as the biosphere. That is what composes the biosphere. And then what is cryosphere? What do we understand when we talk about cryosphere? Cryosphere represents the frozen regions of the planet. That is, the polar areas, they are frozen. The third pole, the Himalayan region, which consists of one of the largest masses of ice outside the North and the South Pole, that is also a frozen area. So, all these basically are included in the portion of cryosphere. It is the interplay between these systems which are responsible for the conditions that we see around us and the conditions in which we tend to live. Okay. Now, here we talk about, first of all, the basic terminologies that you will come across in the portion of geomorphology. And when we talk about the portion of geomorphology here, you come across lofty peaks, very lofty pointed peaks. These are your mountains. So this is the image of Mount Everest, the tallest mountain peak across the planet. So this is your mountain. So in the case of a mountain, you'll find certain features. For example, you will find that in the case of a mountain, the peak is always pointed. It will have a conical and a pointed peak out there, right? It will generally have sharp edges around it, and it will end up having a kind of a distinct conical peak. It is going to be very high. The gradient, the slope is going to be very steep here. Okay. So basically, in this case, you'll find greater height, then, for example, you'll find the presence of conical peak, steep slopes. These will be your features. Okay. Okay. Before I forget, an announcement for all of you that those of you who would have attended the morning sessions and the morning batches of geography, on Saturday we will be having the session from 7:30 to discuss about the maps, and the doubt clearing session that will be held on Saturday from 7:30 a.m. up till around 11:30 and 12. So, whatever doubts that you have had till now, please do send it over to us by mail at IES Live, and we shall be resolving those doubts on Saturday. Other than that, we will be taking up the discussions for mapping. Okay. Now, here, that is the case of a mountain. Now, here, from the top of the mountains, generally the mountains have such greater height that everything will be frozen, in the sense that water will not exist. Water will exist in solid state, that is in the form of ice. So everything is, that is why, frozen beyond a particular height. Now, after that, at that particular height, you will find that as this ice accumulates, this ice tends to move ever so slowly, aided by the influence of gravity. Aided by the influence of gravity, that ice starts moving down the slope ever so slowly. Now, what are these known as? These are known as glaciers. Glaciers are basically your moving mass of ice which comes down the slope consistently with the influence of gravity. These eventual glaciers, when they reach the lower portion closer to the sea level, that is when that ice starts to melt, and that is what feeds the water and gives water for the various river systems that drain the various large areas across the surface. So that is the work done by the glaciers. Now, another feature that you come across quite frequently is that of a hill. So when we talk about a hill, oftentimes you hear about the term hill, right? The Nilgiri Hills, the Satmala Hills, etc. What are these hills? So hills, they are nowhere as high as the mountain. They will generally have a kind of a rounded top, right? Gentle slope feature, which is not going to be very, very steep, a very gentle slope, and a kind of a rounded feature will be in existence. That is the case of a hill. Okay. Now, this is what is referred to as a plateau. A plateau is basically a flat tableland like structure generally created out of volcanic eruptions. So, a flat tableland like structure, tableland like structure. When we talk about how volcanoes erupt, what is the process of eruption of volcanoes, there we will be talking about that how these many of the plateaus also get created. But when we say flat tableland like structure, so flat surface and steep sides, generally created due to spread of molten lava. That is how the plateau like structures they eventually get created. Okay, for example, in the southern part of our country, we have the Peninsula Plateau, the Deccan Plateau. That is basically this kind of a flat tableland like structure which is in existence. Okay, so you will have steeper sides and flattish top surface. That will be the case of plateau. So we will be talking more about it in the coming days about how, for example, a mountain, when it is created, at that point of time it is very high, conical. You have glaciers and ice on top, and over a period of time the top portion is eroded, removed away by the winds, rivers, etc., and you have the formation of a hill. For example, in the region of Rajasthan, you have the presence of the Aravalis. All of you would have heard about the Aravali Hills, right? Now, as of now, if you think about Aravalis, the Aravalis they have not got a significant amount of height. The Aravalis basically they have got very limited amount of height. And if you take a look, those of you who have visited that place or those of you who have lived in that region, you would always be able to understand and identify it with the fact that you can basically climb up the Aravalis in half a day and come back again. Now, if I tell you that at one point of time in the history of planet Earth, Aravalis were amongst the tallest mountains across the globe. At one point of time, Aravalis had the top peak of it covered with ice and glaciers. You had various glaciers which would originate from the Aravalis and they would continue to come down. But look at it now. So, the mountains, they are created by the internal movement of the planet Earth. The internal forces of the planet Earth, they end up creating and carving out these top mountains, high mountains. But as soon as the internal forces they weaken, then these get eroded and these get reduced to a kind of a small feature, what you refer to as a kind of a hill. So, the Himalayas, as we talk about the region of Himalayas, presently you would hear that Himalayas are the tallest peaks of the world. Fair enough. But that is consistently being uplifted by the interior forces acting across the planet Earth, which we'll study about in detail. We'll study about all these things in detail. Don't worry. We'll study about glaciers also, mountains also, hills also, plateau also. Everything we'll study in detail. This is just your introductory image so that you have some image in your mind, so that when there is a cross referencing, or in the other areas, whenever there is a referencing, you can identify that, okay, glacier is a moving block of ice coming down the slope. Okay, so that is where all the various different features on the land surface, they are acted upon by the forces coming from the interior and coming from the outside surface, such as wind action, river action, etc. Now, that study of the change in landform that we experience around ourselves, that is what is included in the portion of geomorphology. That is what we have to study in the portion of geomorphology. But before we study about these various different forces, the change in the landforms and the change in the land patterns, first of all, let us make ourselves familiar with the aspect of formation of Earth. How is it that Earth came into existence? Bhimare, steep side means that the slope is significant. It is like this. So that is steepness. Gentle means like this. Steep is like this. Megha, how Earth is created, sir? Understand, sir, how Earth is created, sir? Okay. Isn't that what we are talking about, Megha? So, okay. I sometimes fail to understand the questions. Uh, I'm not getting hill. Hills are, see, if this is a mountain, this will be a hill. Okay? Much smaller form, a kind of rounded peak, that is your hill. Glaciers are at the peak of the mountains, at the top portion of the mountains, yes. That mean west of ideal is running 1 day, yes. Shweta, what is cryosphere? The frozen areas, the areas which are frozen, North Pole, South Pole, the region of the Himalayas, the frozen areas. So Megha, I hope that doubt was something else. I am unable to understand what is your doubt here. Can hill turn into a mountain? Yes, it can. Over a period of time, maybe the internal forces will activate its motion, and then again, its height will increase. Okay. So basically, GMT is the Greenwich Mean Time, that is referred to as the case of the Greenwich Mean Time. Basically is the reference time with respect to what we have the reference of time zones across the world. When we say that, what is the Indian Standard Time? How do you measure what is the time standard time of India? Obviously, you will need a reference pointer. You will need a reference pointer. So that reference pointer is your GMT. Now we talk about the case of formation of planet Earth. Now, planet Earth, just like the solar system, came into existence around 4.5 billion years ago. 4.5 billion years back, you had the formation of the star, that is the sun. And basically, it was created as a result of the gases of hydrogen coming together, the molecules of hydrogen coming together, producing significant amount of energy, and thereby in the process producing helium. Right? So you had molecules of hydrogen forming helium. So that would be the case of the process of formation. So here, of formation of the sun. Now, that those gases, what you would have studied as nuclear fusion, where two small molecules come together, produce enough heat and energy, and that is where the sun gains its energy by the process of nuclear fusion. But around 4.5 billion years ago, you did not have any planets in the solar system. You just had lot of small particles moving around of various different types of elements, etc. Small dust particles moving around. Now, this entire process of formation of planet Earth is basically driven by certain basic principles. What are those basic principles? Any object which has got mass will have a gravitational pull of attraction. Heavier the object, greater will be the gravitational pull of attraction. Lighter the object, less will be the gravitational pull of attraction. Any object which has got any amount of mass, that will try to pull the other objects by the force of gravity. Okay, it will try to pull the other objects. Now, also, another basic principle, whenever you have two objects which will collide, now during the time of collision, heat is produced. Heat as an energy is produced always. Okay, so with that, let us understand the concept of formation. So, first of all, around 4.5 billion years ago, you had the sun, which had been formed, and it was significantly unstable at that point of time. Even sun was not very stable, and you had many millions, billions, trillions, and trillions of dust particles, which would simply be moving around the sun. Obviously, by the gravitational pull of the sun, they would be moving around the region of the sun. Okay. They would be moving around the region of the sun consistently in a very large area. Now, these were objects of different sizes, but none of them were very large. They were very small. So that is where they would consistently be moving around the region of the sun, and all of them would be in motion, obviously aided by the gravitational pull of attraction of the sun. So when you have multiple particles, millions and trillions of these particles moving around the region of the sun, you would have the situation where there would be multiple such collisions. Hundreds of trillions and trillions and trillions of these collisions would happen every day, because the particles would invariably come into the path of each other. And as I told you, at this point of time, the solar system was not very stable, the sun was not very stable. Okay, so these were the particles which would continue to move around the region of the sun. Now, here, as they would move, there would be collision. And understand that the collision is also of various types. Let's suppose two objects, they simply come and collide like this. Now, it can disintegrate, it can virtually disintegrate into various small pieces. But what if an object is moving like this and another object goes for a collision? An object continues to move, and meanwhile, another object coming at a faster speed, it undergoes a collision. In that case, what will happen? It won't disintegrate. It will basically, the collision will produce enough amount of heat, and due to that heat, maybe the objects will get together, isn't it? So the objects would get together after each collision. So you had a kind of a chain reaction. What was that chain reaction? So collisions of particles would happen. These collisions of particles would eventually produce heat. Due to that heat which would be produced, particles could join each other and form a larger mass, right? Because of the heat that is produced, they would basically melt around the region of collision and they would combine and then they would start moving. So when they would join to form particles of a larger mass, larger particles having greater gravitational pull would be formed. Isn't it? Larger particles having a much greater gravitational pull would be formed. And that means these particles would start attracting the other smaller ones. And that would lead to more collisions, isn't it? More collisions would happen. Again, heat would be produced. Again, more particles would come together. So, like that, slowly and steadily, large sized particles started getting created around the region of the solar system. Very large sized particles, they started getting created. Now, with each of these collisions, as the particle size grew larger, with each of the collisions, the particle would develop a kind of a movement, a kind of a rotation amongst itself, and they would continue to move around the sun. Now, as the size would increase, so rather than having a random motion of the particles, they would now be pulled more strongly by the sun and they would start moving in a fixed path and a fixed pattern. Slowly and steadily, this led to the creation and the formation of very, very large sized objects, which we refer to as planetesimals. So, this process created very large sized particles or very large sized objects known as planetesimals. These planetesimals would continue to move around the sun. Okay, they would continue to move around the sun. Now, still, you had many of these planetesimals moving around the sun. Now, then came the next stage. So, now, when you talk about the region of the sun, basically, the sun would be surrounded by large planetesimals, which would basically be moving. Large planetesimals, which would be moving around the region of the sun. Now, obviously, these would consist of various different materials and elements which would be created right at the time of its formation. And the properties of these dust particles, eventually, depending upon what kind of materials were present, many of the new elements were also created. But you had various different particles which would be consistently moving. These would be your planetesimals. Now, these planetesimals, which would be at various different distances from the sun, they had significant amount of mass, significant amount of gravitational pull. And that is when they would collide. One or the other would come in the path of each other because the solar system, again, remember, was in its very formative stages 4.5 billion years ago. Solar system was in its very formative stages. Solar system had not evolved. So that is why it was unstable. And many of these planetesimals would be floating around. It was nowhere close to the solar system that you see today. Now, these planetesimals, they underwent multiple different collisions. and each of these collisions would produce a lot of heat. And with each of the collision, these planetesimals would get a kind of a spin associated with them. They would have a certain axis which would be created with each collisions, right? Eventually, the heat due to these collisions would be so significant it would melt the objects. Multiple of these planetesimals, they would come together, and that led to the formation of the primitive earth. Primitive earth was formed. This is your primitive earth. Earth. Now, this primitive earth that we talk about, this was formed as a result of these multiple collisions of these planetesimals. So the heat produced was very high. As the heat produced was very high, what would that mean? That basically would mean that the materials would get into a kind of a molten state. The materials would start melting. So here, it was nothing but a hot, molten, spherical object. Everything was in a liquid state, molten state, because the temperature was very high. This I'm talking about around 4.5 billion years ago. Now, everything was in a molten state. And you had various different types of elements present. Now, whenever you talk about liquid and different types of liquid, if you mix together, all of them, it is not always going to present a kind of a homogeneous mixture. For example, if in a glass jar you pour water, you pour honey, and you pour oil. Let's suppose you pour honey also, you pour water also, and you pour oil also. Now, will all of them form a good solution? Will all of them be able to mix uniformly? Absolutely not. Honey, being the heaviest one, will settle at the bottom, then will come water, a layer of water, then will come a layer of oil. So, at this stage, the heaviest elements which were present at this stage, they started settling at the bottom. The heaviest elements which were present at this stage, they started settling at the bottom. So here, the heaviest elements, and at this point of time, heaviest elements which were present were iron and nickel elements started settling to the bottom. Okay, they started settling to the bottom. So, for example, if let's suppose you had, now by the way, again another thing that students sadly they get confused in this, when I say bottom of the planet earth, what do I mean? Do I mean this point A, or do I mean this point B? What is the bottom of earth? Okay. This is what I was afraid of. Okay. So when you think about the region of Antarctica, guys, what is the imagination that you have? People are standing upside down in the region of Antarctica. If you go to Antarctica, do you think people have to stand upside down? Is that the kind of an imagination that you have? That it is the bottom of the planet Earth. So someone who is standing here will simply fall off into the outer space. Is that the case? All of those who said that bottom is at B, I won't be naming you guys, but think about it for a brief moment. How do you think that bottom bottom would be at this region. Bottom is always around the region of the center, the core. Okay, from all sides, if you go to the bottom, from all different sides, if you go to the bottom, you will reach the region of the core. You will reach the center. So bottom is always the center. That is core of the earth. And at that point of time, the heaviest elements were iron and nickel. That is what started settling to the region of bottom. And that formed the core. Even today, when you talk about the core of planet Earth, even today, the core is consisted of mainly iron and nickel is what dominates the core of planet Earth even up till today. Right? So that is how basically you had the earliest formative portion of planet Earth. But still, the solar system was not stable at this point of time. You still had millions and thousands and millions of collisions happening with this molten portion, where you had small objects continuously crashing into this molten portion, getting melted down as well, and adding to the portion of planet Earth. At this point of time, you had another massive collision which happened, and collision with respect to planet Earth, another massive collision which happened. So, here, when you talk about the collision, you had a Mars sized object, a large Mars sized object, which was coming in the path of planet Earth. A large Mars sized object. Sized object coming and colliding with molten Earth. This large Mars-sized object, this was named as Theia. Mars-sized object, what are the interpretations of Mars-sized object? What what is the English meaning of Mars-sized object? Think about it. What can be the meaning of it? Means an object which has a size, which had a size which was similar to the size of Mars. That is what is the meaning of Mars-sized object. Is that difficult to understand? Okay, I hope that is not difficult to understand. Basically, that Mars-sized object came and collided with planet Earth. Now that collision was huge. Earth was in a molten state, and this object went and simply crashed onto the planet. So this object also got disintegrated. Some portion of it was thrown away. And along with that, many of the molten portions of the planet, they were also thrown away. Along with the objects of Theia, many of these molten objects, they were also thrown away. But then, planet Earth by that point of time had become so large that its gravitational pull of attraction was very significant. And it basically could take away the top surface, the top portions of planet Earth. The molten, it was molten obviously. So the top portion basically was carried. Imagine a large ball which is molten and another object which comes with a force and crashes with that. So some of that other object, foreign object, will also get dismembered. Some of that foreign object will also go away. Along with that, lot of molten particles on the surface will be splashed away. It will create a huge splash. A lot of these materials will be thrown away. But by that point of time, the planet Earth had got a very distinct gravitational pull of attraction. So, that gravitational pull of attraction meant that planet Earth did not let these molten particles fly very far away. And these molten particles, they were held by Earth's gravitational pull. Slowly and steadily, it was continuously held because of the Earth's gravitational pull. And it would continue to move around the planet Earth owing to the momentum of that crash. That object, which is held or which was held by planet Earth due to its gravitation, is still held by planet Earth due to its gravitation, and still today, that object continues to move around the Earth's surface. And that is what we refer to as the moon. That is how moon was created. So moon was created as a result of a very giant and a big impact. And that is why formation of moon is what is also referred to as or provided by giant impact hypothesis. It was that giant impact which with Theia which led to the formation of moon. How do we know that? How do we know what happened 4.5 billion years ago? It was only in the last century or in the last few decades when the Apollo missions, when they went to the moon, they brought certain rock samples. And analyzing those rock samples, one got an idea about how these would have been created. They have the same origin, same time scale of origin as compared to the planet Earth. And basically, few of the rock particles, they have the evidence of some foreign object as well. So that is basically also tells us analysis of the particles of the moon. That tells us that it is only the lighter portions and the lighter particles of planet Earth which were carried away and led to the formation of the moon. And that is after the Apollo missions of the 70s and the 80s. That is when we came to the conclusion that this is how the moon could be formed. Recent findings have indicated something very unique. By various seismic waves and instruments by which we study the interior of the earth, it has been found that underneath the region of Africa, you have the evidence of this Theia. Underneath the region of Pacific, you have still a very hard solid mass, very deep obviously in the interior, which tells you that as this Theia would have come and crashed onto the planet, some portion of it would have flung away, but it would have disintegrated, it would have broken into two larger pieces, and because the planet Earth was molten, it started settling down and sinking in the interior. It is still to be found underneath the region of Africa and underneath the region of the Pacific. Now, don't get here childish ideas that does that mean that if we dig a hole in Africa, we will get to look at Theia? We are talking about great depths of many hundred kilometers deep where you will have the evidence of this. Okay, so that is how the planet Earth came into existence, and that is how the moon was created. But after this, still the planet Earth was in a molten state. And by this point of time, the heaviest elements had settled to the center, that is the core. But what about the other state of planet Earth? We do know that planet Earth is no longer in a molten state. We do know that we refer to planet Earth as a kind of a blue planet. How is it that Earth basically became a blue planet? So, then came the process of evolution of planet Earth. This is the basic formation. Then came the evolution of planet Earth. So let us talk about the evolution of planet Earth. So observe here Basically, in the time of formation, you had multiple of these planetesimals which crashed together, produced enough heat. They got together, formed a larger particle, which would then move, crash with the other ones. And that was the process of formation. But when we talk about evolution of Earth, how did that happen? So, planet Earth was in a molten state. Heaviest elements had settled at the bottom. Slowly and steadily, the number of collisions across the solar system reduced drastically because most of the smaller particles were already undergoing collisions somewhere or the else. So slowly and steadily, number of collisions they came down. They basically were reduced. And eventually, you had this as the planet Earth, which started becoming stabilized. And when the number of collisions reduced across the solar system, planet Earth also experienced some amount of cooling. Now, it was a hot, molten liquid ball of mass. So think about it. Cooling would happen from the outside or cooling would happen from the inside. What do you think? Would the cooling happen from outside or would the cooling happen from inside? Very good. Cooling would always happen from outside because it is from the outside that it is in contact with the colder areas outside. Inside, it is very hot. So, cooling started happening from the outside. For example, when you boil milk, right, when you shut off the stove, after some time, if you touch the surface, it is slightly cooler. But if you dip your finger into the milk, the interior portion of it is very, very hot. Isn't it? The interior portion of it is significantly boiling hot. So that means the interior is very hot, the surface is cooler. So cooling always happens from the surface. Here also, the cooling started to happen from the surface. And that is when, as it cools, it starts developing some wrinkles, few areas they remain in an uplifted portion, few of the areas they get depressed, because that is how it cools. Even when you let's say we talk about the cooled portion of milk, when the milk cools down, you will observe that the top surface of it develops a thin solid layer, which is not going to be always plain. It will have some wrinkles developed into it. So that is when slight wrinkles developed. Few of the portions they had depressions, few of the portions they had some amount of upliftment. But in the interior, the temperature was still very high. So here, cooling started to happen. Cooling was initiated from outside and the interior remained very hot. Even today, we have the same scenario. The interior of Earth is still very hot. And over the next 3 to 4 classes, we will see that all these events, earthquakes, volcanoes, formation of mountains, creation of oceanic trenches, everything is basically driven by the interior heat of planet Earth. That heat still remains in the interior. Now, that heat which remains in the interior, which still drives the major forces of the planet, for example, formation of plateaus. I hope you are aware. If you are not aware, most of you would not be aware, in fact. Every few areas and after every few million years, due to the internal heat of planet Earth, you know what happens? The land simply gets pushed up in certain areas. The land simply gets uplifted. And that is, if you have to think about it like, for example, you have some solid substance, any solid substance. iron, any of that, plastic. If you provide heat from inside, it swells up. It kinds of gets inflated, isn't it? Something similar happens on the Earth's surface also. Because the heat in the interior is so high, every few years, rather, when we say few years in geography, it is not like history or other subjects. Here, every few years, we are talking about every few millions of years, hundreds of millions of years. The land simply gets uplifted. Sometimes, due to the heat, the land simply comes down. So, that heat is still a dominant factor across the various parts of the planet. This is what is also known as the residual heat, or the heat which remained. So, this is known as residual heat. That is what we consider and what we know as the residual heat. Now, in this case, the cooling had been initiated from outside, and in the interior, everything was still molten. Slowly and steadily from outside, things started cooling down. By cooling down, if a liquid cools down, it becomes a solid. So, slowly and steadily from the outside, things started getting into a solidified state. Rocks started getting created. Earliest rocks got created. And we have evidence of that. Rocks dating back around 3.5 billion years ago. We have the evidence of that. Certain areas in Australia, the rocks have an age of around 3.5 billion years old. Forget Australia. In India, when we talk about the region of Jharkhand, the Chota Nagpur Plateau, you have the evidence which indicates that might very well have been amongst the first few land masses the planet had witnessed. But we'll come to that. We'll come to the formation, creation of land masses. Now, still in the interior, many materials, different types of materials were in a molten state. And along with that, you had gases. Molten materials and gases were trapped inside. Okay? Molten materials and gases were trapped inside. Now, here you might have a doubt. How come gases? It is okay as long as you were telling me that molten material, I could still wrap my hand around it. But how come gases? So think about it. When we talk about any kind of material, let's suppose alumina. Alumina is what? Or silica. Silica is SiO2, iron oxide, Fe2O3, hydroxides, OH. Right. Now, if you basically melt this, SiO2, silica is in a solid state. The sand particles that you have, that consists of silica, it is in a solid state. But it has got oxides. If you melt it, what will happen to the oxygen? Oxygen will get converted into gas. Right? Oxygen will get converted into gas. So, like that, you had various different gases which were trapped inside, and the outside had started solidifying. But it was still solidifying. The outside surface was nowhere as strong as what we have today. It was still solidifying. It was in the process of solidification. So that is when the earth went through a phase, what is known as the phase of degasification, where from various different areas, these gases are always lighter, isn't it? Gases are basically lighter. So, being lighter, they will try to rise to the surface, and they will bring the molten materials along with them. So, the gases, they started exiting the interior of the planet. And the surface was not very hard. Again, recall the moment when you have basically just had some amount of cool milk. So, on that case, you have the surface, which develops a very thin solid layer. But if you poke your finger into it, that solid can easily be broken. Right. So, that was the condition of the Earth's surface. It was solid, but not very hard. The planet entered into the phase of degasification. Phase of degasification. Now, when we say a phase of degasification, what do we mean by that? We basically mean that the gases trapped in the interior, they started erupting out. They started moving out of the interior. They broke through the surface, bringing molten materials again to the surface. So you had millions and billions of volcanic eruptions which would happen. A lot of volcanic eruptions would happen on a daily basis in different parts of the planet. So, gases trapped in the interior, trapped in the interior, started to escape, which brought the molten materials along in the form of multiple volcanic eruptions. Multiple such volcanic eruptions happening on a daily basis. Now, amongst these gases, few of the important gases also escaped. And when I say few of the important gases, you had gases such as ammonia. Ammonia was one of those gases. Methane was one of those gases. So you had NH3, CO2, CH4, O2, oxygen as a gas was released. Along with that, you had sulfur, sulfates, significant amount of hydrogen. Now, hydrogen and oxygen at that high temperature would fuse together. And that is what led to the formation of water vapor. Vapor, H2O, would also be released. Now, these gases started circulating in the atmosphere. And this period, by the way, this continued for many millions of years. We see a volcanic eruption nowadays. We think about it, oh my God, what is happening to the planet? Are the gods angry with us? That volcanic eruption has been continuing for a month. Think about a period and try to imagine a period in planet's history where these eruptions would continue, not only for a few months, not only for a few years, not only for a few centuries, not only for a few millennium, for hundreds and thousands of years, multiple times of that for many millions of years, you had this consistent amount of gases getting released because Earth is a massive object. So, that phase of degasification expelled these gases from the interior. Then, for a brief period, there was a kind of a lull. Lull, as in, you did not have many of the volcanic eruptions at that point of time. So, again, that process of cooling down accelerated. So, then as the process of cooling down continued. So that is when phase of cooling. Again, this phase of cooling down accelerated, where if you consider the planet Earth, now the outer surface started solidifying. Further significantly, it was already a solid with various different types of deeper areas, uprised areas, etc. But that was it. Barren rocks were present. That's it. And over the period of many millions of years, as these gases they would surround, the phase of cooling happened. Now, it was in this phase of cooling when water vapor combined with gases, ammonia, dust particles, etc., and they started forming dense clouds. Very significantly dense clouds were created. Very, very thick, dense clouds were created. And these clouds would virtually wrap the entire planet within itself. Now, think about it. A planet which is cooling down now has got that cloud cover. So, sunlight is blocked almost perpetually. That is when these clouds cool down even further. And then came the phase of torrential rainfall. Phase of torrential. Torrential means torrential means what? Torrential means something which is very heavy, which is very continuous. That phase of torrential rains, again, how these clouds were created? These clouds were created as these gases they started emerging. These gases they started emerging. You had water vapor, etc. As this cooling accelerated, these gases they formed clouds. So let me write down here itself. So gases cool down to form very dense clouds. Now, further that cooling was accelerated because it would hide the planet from sun. Continued darkness, it became cooler and cooler. And then it rained. It rained and it rained and it rained. In whichever area that you are living in, if it rains for one day, everything becomes very damp and wet. If it rains for 4 to 5 days, whichever region you are living in starts getting flooded. Imagine a rainfall which continued for continuously around thousands of years. Few estimates tell us that it rained for around 2 million years continuously. But many of the geographers don't agree with that. But the conservative estimate is that it rained continuously for close to around 10,000 years. All the ammonia, then you had sulfates, carbonates, everything, methane, everything combined with water, and it continued to rain. So, this was a phase of torrential rainfall where it continued to rain for 7,000 to 10,000 years. That means what? All the low lying areas that got filled with water, and it continued to get filled with water. You had the formation of the oceans and the seas of the planet. And that further accelerated the rate of cooling. The surface started getting harder and harder. And eventually, the interior, from the surface that cooling happened, and the outer surface cooled, the middle surface cooled, but the interior was where the heat remained trapped. Because as the outer surface cooled, there was not many areas from which the interior molten heat could escape. So the heat got trapped in the interior. The heat remains trapped till today in the interior. That is the residual heat. So this basically accelerated, this not only filled up the seas and oceans, and accelerated the rate of cooling. In the interior, you still had the portion which was molten, and in the interior, you still had basically the presence of that heat, which is referred to as residual heat, which continues to remain trapped even today. So, almost around 3.8 to 4 billion years ago, that is around half a billion years since its formation. Half a billion years is not a short span of time. This entire thing happened around 700 million years to 800 million years, we are talking about. In that 700 to 800 million years, these things happened. And that is when the planet started to settle down. And around 3.5 billion years ago, you had the germination of life. Life started because the ground surface was still very a harsh condition, very harsh. Ground surface would still experience volcanic eruptions here and there. There was nothing but hard rocks. But oceans, they represented a kind of a calm condition. Oceans represented a region of calmness. That is where small celled chemotrophs, that is, those microbes which can utilize the chemicals around them to produce food, these chemotrophs, they started coming into existence. And that was the genesis of life. That is how life originated. And for the next couple of billions of years, life existed only underwater. It is only when you would study in the portion of environment, it is only when the conditions started becoming harsher in the oceans, life migrated to the land. But for a long period of time, life remained only underwater. Slowly and steadily, when these microbes, they found out that okay, carbon dioxide is present in a dissolved state in the water, they could basically use that carbon dioxide, oxidize it, get enough food, manufacture carbohydrates. They could sustain themselves. When they could sustain themselves, they would multiply. Like that, multicellular organisms came into existence. You had some of the, and generally most of these organisms would be situated in the shallower areas of the oceans. That is where the water would not be very deep. Still, the deeper parts of the ocean is said to have been denied of any form of life because the conditions at the bottom were also very harsh. That is how the planet Earth came into existence. And this entire journey, which has happened over the span of 4.5 billion years, that is very unique, where you will find that the planet has not been disturbed by a major massive collision. ever since that time of uncertainty around 4.5 to 4 billion years ago, planet has not been disturbed by a major massive collision until around 65 million years ago, when you had another such massive asteroid, which basically came into the path and collided with planet Earth. And that created havoc. That put to an end to the most dominant species that planet Earth had ever witnessed, in the form of dinosaurs. Otherwise, if that collision would not have happened, maybe you and I, we would never have been in existence. We would still be living in the era of dinosaurs. And one of the latest research papers, which has been published only this month, it basically tells us that the only reason that we mammals, we basically we do not have a long lifespan. We have a very short lifespan. We end up maturing, and basically the reproduction happens, and we end up dying by the age of 60 or 70 years, is because of the dominance of dinosaurs. It was because of the dominance of dinosaurs that the mammals, they learned that if you have to survive, reproduce fast, because you never know when you might die, you might be consumed. That asteroid, which collided with the planet Earth 65 million years ago, that took care of it. And now we mammals, we dominate the planet Earth. So that is about the entire evolution and formation of planet Earth. Now, the formation and evolution of atmosphere, we will study in the portion of climatology. Now, direct question is never asked in general studies that talk about the formation of planet Earth. That direct question will not be asked in GS. Here, you can have a pinpointed statement being asked from it. For example, you can have a question that oxygen was always present in the atmosphere of planet Earth right since its formation. Will that be a correct statement, or will that be a false statement? What do you think? Oxygen has always been present in the planet's atmosphere right since the time of formation of planet Earth. False, right? So, this was a question which was asked in 2018 prelims examination. So, if you understand this process of formation, as we move ahead into the interior, even that would be understood very easily. Okay, so a quick recap. Basically, what started? It started with the formation of the sun. How did the sun come into existence? You had the gases of the lightest elements of hydrogen came together. Nuclear fusion happened. Hydrogen collided to form helium, right? Nuclear fusion reactors you would have studied. So that produced heat, energy. Sun started getting created. Large mass, it had its own gravitational pull. Various dust particles were floating around. As these dust particles were orbiting across the sun, then they went through multiple of such collisions. With each collision, there would be heat which would be produced. The size of the particles would continue to grow larger and larger and larger. As these particles would continue to grow larger, they would have their own gravitational influence. They would have their own gravitational force of attraction. And that gravitational force of attraction, or that gravitational pull, would lead to more collisions. Eventually, they led to the formation of those early objects, which are referred to as the building blocks of these planets. That is what we refer to as planetesimals. These planetesimals, they came together and they collided to form the planet Earth. And like that, many different planets. And that is when, as the planet Earth got created, at that point of time, the heat was so high that it was in a hot molten state. Heaviest elements of that point of time, that is iron and nickel, they started settling down. They settled down at the region of the bottom of the Earth, that is the core of the Earth. And it still forms the dominant portion of the core of planet Earth. Then after that, as these number of collisions they reduced, planets started becoming stable. But as it was happening, a very large object almost to the size of the Mars that came and collided with the Earth. That object was named as Theia. Now, due to that giant impact, portions of the top surface of Earth were basically removed off, and it continues to orbit around the Earth even today, and that is the moon. That is why the formation of moon is referred to by or can be understood by the giant impact hypothesis. After that, again, as the planet became stable, it started to cool down from outside. The surface started to cool down, but you had so much amount of molten materials and gases which were trapped in the interior that the gases wanted to exit. The gases, they tried to escape. As these gases would try to escape, they would basically puncture the surface and emerge outside. And you had the phase of degasification dotted with hundreds of millions of volcanoes and volcanic eruptions continuing for many millions of years. It was at that point of time when you had gases such as methane, carbon dioxide, oxygen, hydrogen, some amount of oxygen, not in the quantity that you find today, for a long period or up till very recently. That is up till around 300, 400 million years ago, 400 million years ago. Oxygen was amongst the little amount or the minor gas which you would find in the atmosphere. Now, at high temperatures which were prevalent, oxygen and hydrogen combined to form water vapor. You had so many dust particles emanated outside because of these volcanic eruptions. Oxygen, hydrogen, etc., they combined to form the earliest clouds. Those clouds would consist of various gases, ammonia, methane, etc. And after that, when that phase of volcanic eruption stopped, again that process of cooling was reinitiated. During that cooling, cloud formation became prominent. You had a very thick cloud cover which covered the entirety of the planet Earth. And then it rained. It rained, it rained, and it rained for thousands of years. And that is what filled up the earliest of the seas and the oceans. And that is when the planet was basically converted into a blue planet. And basically, after that phase of torrential rainfall, that cooling accelerated, reducing the heat trapped in the interior to the region around the core and the region somewhere around the mantle. But rest of it, the entirety of mantle and the top portion were solidified, and in the interior, it is still in the molten state. That is the residual heat. So that is the entire process of formation of planet Earth. Okay? I hope that is understood. Right? Now, after this, we move ahead to the portion of the interior of Earth. So basically, when we talk about the interior of Earth, now about the question that where did iron come from, where did these elements come from? So all these dust particles which were there, they had the presence of few of these elements, many of these elements. That is why you send the space probes. You recently had the space probe which went to the asteroid and collected some particles from asteroid and returned to the planet Earth. Right, it is from this analysis, the earliest particles that we get an idea about what would be the condition of the particles which would have collided. So these elements were brought by the collisions. Okay. Now, after this, you have the case of interior of the Earth and the interior structure of planet Earth. So when we talk about the interior of Earth, what is present in the interior? Or what is the structure of planet Earth? So the structure of planet is still collision taking place. Have you heard about a collision taking place around you, my dear friend? Have you experienced a collision in your area now? You still have objects which come, few of the collisions which still happen, but now the solar system has settled down. Now you don't have many objects moving around. It is only between Mars and Jupiter where still you have a lot of particles moving around, that is the asteroid belt. But other than that, the solar system has largely settled down, so obviously no particular collisions. Now, After we move ahead to the portion of interior. When we talk about the interior of planet Earth, here it is always likened to that of a structure of a coconut. Now, all of you would have seen coconut, the ripened coconut, basically where the outer structure, the outer part of it, that is hard, but it can break easily. Then you have the inner whitish shell, isn't it? That whitish shell or the inner whitish layer, the pulp of the coconut, that is solid. But it is that kind of a solid. If you press it, it can be compressed. If you stretch it slightly, it can be stretched, isn't it? That is the region of the mantle. And then the coconut in the inside consists of liquid. Like that, planet Earth in the inside also consists of molten materials. So that is why the interior structure of planet Earth is always likened to that of a coconut. But how do we get to know what is present in the interior? Has someone gone to the deeper portion and to the core of the Earth to find out what is present in the interior? Obviously not. As you start digging into the planet Earth, the temperature starts rising up so significantly. You cannot dig beyond a point. But we have other sources of information. So, many of this idea about what is present in the interior of planet Earth, that started getting clearer in the early 1900s, in the first couple of decades of the 1900s. So here, basically, when we talk about it, the interior of Earth, you have the sources of information. Sources of information for the interior. Now, these sources of information about the interior, they can basically be brought into two parts: direct sources and indirect sources. Okay, when we say direct sources, we are basically talking about where you get the direct evidence of what is present in the interior. For example, volcanic eruptions. Volcanic eruptions. So, volcanic eruptions basically means molten materials from inside they come up. By analysis of that molten materials, we get an idea of what kind be the chemical composition of the materials present in the interior. So that is where the volcanic eruptions, they give us an idea about what is present in the interior. That is why every time when a volcano erupts, you will find various different geologists, scientists, they go with all the protective gear, they go to the site of the volcanic eruption, they start collecting the molten materials, keep it in a bucket, and they analyze it for years altogether. And by that analysis of that solidified material, the particle structure, the chemical composition, the property, they get an idea that this molecule would have experienced what kind of pressure from above, which portion of the interior is this coming from. So, what is the interior of the planet? So, that volcanic eruption is one of the direct sources. Then, other direct sources, or the other direct source is basically mining and digging. But the deepest mines across the planet, they don't go deep enough. When we talk about the radius of planet Earth, are we aware about what is the radius of that spherical Earth? Earth has got a radius of close to around 6,370 kilometers. 6,370 kilometers. That is the radius which carries you to the interior. So if you start digging Imagine how much time will it take for you. And obviously, you are digging into such hard rocks, you won't be able to drill beyond a particular region. The deepest mines, which exist in the region of the Kola Peninsula in the northern portion of Eurasia, the deepest mines have a depth of around 10 to 12 kilometers itself. But that in itself gives you enough idea that as you start going deeper, the temperature increases. As you start going deeper, the materials, they start getting compressed. Different type of materials will be found there. So that is the case of mining and digging. That idea is given to you. Then indirect sources. These are your direct sources, direct set of information. But analysis of many different ideas and many different pieces, they give you an idea about the interior. So what are those indirect sources? So first is seismic waves. Whenever an earthquake occurs, it releases so much amount of energy that the energy travels in the form of waves. We will study later what is known as the seismic waves. Now, these seismic waves, they travel through the portions of the interior of the planet, throughout the portion of interior of the planet. Analysis of the seismic waves give us an idea that from which region have they traveled, that region is in a solid form or a liquid form. We will study more about it when we talk about earthquakes. So indirect sources, seismic waves. Then after that, study of the meteors, the asteroids, because they give you an idea about what the particles moving around the sun 4.5 billion years ago, what they would have looked like. Okay, so it is those collisions which had led to the formation of planet Earth. So an analysis gives you an idea about what that would look like. So there, basically, asteroids and meteors. Then the planet Earth extends a kind of a magnetic property. It behaves like a magnet. So studying the magnetic field gives you an idea that what is present in the interior which extends that magnetic field. We have studied yesterday that the planet Earth is a kind in a shape of a geoid where it is slightly bulged around the region of equator. It is slightly flatter around the region of the poles. So that basically studying the gravitational and the magnetic fields, that gives you an idea about the interior structure and the materials composed in the interior. So here, magnetic and gravitational anomaly. Forces and anomalies. Okay. So with these sources of information, we get some idea about what is present in the interior. Okay. We'll move ahead further with this. Before that, we take a break. So let's take a break and let's be back and we will continue with this discussion. We'll talk about the structure of the interior as we move ahead. So we take a break of 15 minutes. If a small particle is attracted by a large particle due to pull force, why Earth is not pulled by sun? How does the Earth revolve around the sun? What do you think? Is there a heavenly body out there from whose blessings the planet rotates around the sun? What do you think is the force which makes the planet move around the sun? Web of asteroids basically is the asteroids, the study of the asteroids. The asteroids, they still indicate what the earlier solar system would have been, because these have not underwent multiple collisions. The region between Mars and Jupiter, that consists of thousands of asteroids moving together, the asteroid belt as it is referred to. So studying these asteroids basically gives you an idea about what might be present in the interior. If a collision produces heat, then how can moon become so cool? Oh, but what if that collision, so planet Earth was also molten? How is it that we are living on that planet Earth? Why isn't that the ground surface is liquid? Why isn't it that we are sinking to the bottom of the planet? Why are you able to stand on the rocks? So think about it. Collision happened, molten particles were present, but 4.5 billion years have passed. That is why the cooling has happened. Okay, let's take a break and let's be back. confirmation about the audio, please, guys. If the audio is clear, kindly confirm. Thank you. Sashi, while in collision phase, why the moon doesn't cool by rain either? Why does rainfall happen? Rainfall happens because of the presence of water vapor. So if you don't have water vapor, then you won't have rainfall. Moon has got ice. The region where I hope you have followed current affairs significantly, the region where Chandrayaan basically where it landed, Chandrayaan 3, where it landed, that is the region of the south pole of the moon that has got a significant portion of ice. But if it is not heated enough, and if it doesn't have enough atmosphere, it won't have the cloud and the occurrence of rainfall. Okay, right? Abhay, what is the confusion that you have with ideal? See, in case you still find the portion of ideal, etc., a bit difficult to imagine, I would suggest to you that go for the on our YouTube page. We have put animated videos. I have put a certain number of animated videos there, or even in the pre-recorded lecture, I have put an animated video about IDL. So in the our YouTube channel, that is Byju's IAS YouTube channel, Byju's Exam Prep YouTube channel, search for IDL. You will find the animated videos that can also help you. Okay. Today webinar, what's time started? Today webinar 8:30 started. It will start at 8:30. Okay. And we stand in circle surface, but we see a flat surface. Yes. Because you are very insignificant compared to that circle or that sphere. That is why you see the flat surface. If let's suppose you would have been so tall, if your height would have been 2 kilometers, you would have seen the curvature. But if you take a look at the sea, if you have ever been to a region where you have a lighthouse, go stand on the top of the lighthouse. You will be able to observe a slight curvature, ever so apparent. And also think about it. When you take a look at the sea, and if a ship is coming towards you, it is not the bottom of the ship that you are able to see. Initially, you are able to see the top, and then slowly and steadily the lower portions they start appearing. So that tells you that it is curvature. Okay. Why doesn't moon have core? Moon will also have core. It will not be the same as the earth's core, but moon will also have core. Means, is there possibility that in future there is lives in moon? That is what every country is trying to explore. All the countries, if you take a look at their future space missions, China, for example, wants to establish a permanent base on the moon. So moon is considered to be that area where all the countries are trying to establish a base. That is why Chandrayaan 3 was so unique, so special, because it explored the region of that icy area, and it is basically seeking a kind of a future habitation there, so that by that ice, if you have the presence of sun, we have enough technology to convert that ice into maybe water, and then by that water we can produce hydrogen and oxygen that can be used as a fuel to fill up the rockets, which can then propel us to Mars. And then that is the future planning, that in Mars also you will have certain areas. Mars also has some of the frozen ice which is present underneath the surface. So from that, again, you will do the same thing. You will have some habitation, some centers there also, or some base there also, and that can be used for intergalactic travel. That is what the future lies in terms of space exploration. Okay. Please clear my doubt. Okay. What is your doubt? if the moon has come out of earth with the same material, see, this is what I will not always appreciate, because it is the initial sessions of the module. So on 709 you have sent a question, and on 710 please clear my doubt. All the doubts will be taken care of. But if you start putting up that kind of a repetitive thing, I will ensure that the only the SMEs will take your doubt. I won't take your doubt. So be patient and ask that question. Okay. So if moon has come out of earth with the same material, then why does it also become the same planet as earth? Okay. Now listen to this carefully. It is a kind of a basic science. So when we talk about earth, if the atmosphere would not have been present, then would planet earth have the green conditions, the ice, etc., that you see? No, it would not have the water, etc. It would not have been present. Plants, I hope you are aware, it is not as if the planet got into existence and plants were first things, that a mango tree came up, and then there was mango tree, apple tree, and then people came and lived there. No, basically, if you think about it, our atmosphere has got a substantial role to play in terms of shaping the life on the planet. Why is it that atmosphere came in is there? Why isn't it that the gases escape into the outer space? It is bound by the gravitational pull of the earth. It is the gravitational pull of the earth which holds the gases. Moon has got a mass which is 1/6 of planet earth. So the gravitational force of attraction by moon will also be very less. That is why in the case of moon, you don't have that persistent atmosphere. Everything has escaped into the outer space. If you don't have that atmosphere, what is going to trap heat? And in the portion of climatology, we'll study about this also, that the only reason that planet Earth is able to maintain that heat, that temperature, is because of the presence of atmosphere, the gases, the greenhouse effect. Now, every few million years, the planet goes through a phase where carbon dioxide moves in abundance in the atmosphere. And whenever that happens, there is heating. Otherwise, in moon also, the daytime temperature is high, but the nighttime temperature goes to around minus 200 degrees Celsius, because there is no gas there to trap that heat. Why is there no gas there? Because the gravitational pull is so very low that everything has escaped into the outer space. Okay, right? Why doesn't moon, because why doesn't moon have heated molten? So if I take a look at all the questions and the aspect of it, most of you are worried about the same thing, that you are saying that moon has separated from planet earth, but moon is different, earth is different. How can you say that from the same thing? Basically, when you have a child which is born out of your human, so that also looks like human. Why isn't it the case that moon also looks like the earth? Right? Many of you have that same kind of a doubt, that heat retained in the interior. Why doesn't moon have heated molten core? All of that is the same kind of a doubt. Because first of all, moon is very small. It consists of only some materials from the exterior. Life that you see, when you liken it to the portion of earth, I'm sure you are not thinking about the mineral composition of the moon here. I am sure that is not your kind of doubt there. Your doubt basically is that why doesn't moon have life? If I'm not wrong, that is that is basically the doubt that you have. That is basically because the moon doesn't have the gases, atmospheric gases. Why it doesn't have the atmospheric gases? Because it has escaped. And that is why when the moon cooled down, the small portion, the small size of the moon cooled down, it could cool down much more quicker. In the portion of planet Earth, it was so very large that the interior maintained its heat, retained its heat. Okay. Seema, if the moon is not a star, why it shines? So does the moon shine equally every day, Seema? Please don't say yes there. I will be heavily disappointed. Moon basically shines because of the light that it reflects from the sun. The solar rays fall on the moon and that basically is reflected. I hope we are aware that in the night sky, in the evening sky, sometimes you will be able to spot the Mars also. You would be able to spot Jupiter also. That also shines. So it is not a star. But why does it shine? Does it produce enough heat on its own? No, it's simply the reflection of solar rays. Okay, right? Now, the longer questions. Why the shape of Earth is only circular, not in other shapes? What is the shape that you would want the Earth to have? Tell me. I will ensure that that shape is present. But yesterday also I had given you the example anything which rotates continuously. For example, the dough that you take in order to prepare chapatis, etc. Now you rotate that dough, you make it into a sphere. So that dough is of a random shape. How do you make it into a sphere? By continuous rotation. Any molten material, when it continues to rotate, it will take that circular shape. There is no rocket science behind it. Okay. Lakshmi, I told you that yes, we see a flat surface. Uh, at the end of a star, life black hole forms and it has high intensity of gravity and a point singularity. And the Big Bang theory singularity is that is a different singularity there. No, it is a different singularity. So when we talk about is it possible in singularity of black hole singularity and a blast? No, that black hole is different. So when we talk about the singularity which was present earlier, it was a highly condensed material consisting which had very high temperature and very high pressure that exploded. Okay, right? On the Dow, there is force of hand. On the dough, there is a force of hand. So, if simply by application of force of hand, if you could convert it into a sphere, try it today. Take a piece of dough, apply as much pressure as you can. Will it get converted into a sphere? No, you will have to put that rotational motion. So, imagine a liquid which is in outer space is continuously rotating. Can it gain a shape of a cube or a cuboid? No, it will always gain the shape of a sphere, right? You gave the example of coconut, how it is related to the earth. So, in the case of a coconut, the outer shell of it is hard. Okay, it is hard. That relates to the crust. Then the inner portion, the whitish flesh of coconut, that is also solid, but it can be compressed. It can change its shape. The flesh of coconut, if you press the flesh of coconut, it can be pressed. Same is the case with mantle, very dense, but if you it can be compressed, it can be deformed. And then the inner portion of coconut consists of liquid core. Okay, again, please clear my doubt. Okay, what is your doubt? But heat is decreased as surrounding is colder. Then how earth cold core is not cooled? Because as the cooling was happening from the outside, the outer portion solidified. So there was not much of a medium from which heat could escape. How do things cool down? When we say a thing has cooled down, how does it cool down? You take out the heat energy, only then it cools down. But that heat energy got trapped, right? And then things started solidifying. That heat energy further got concentrated. So that is where the heat energy, time and time again, it gets lost. That heat energy, every time that a volcanic eruption happens, some amount of that heat energy is released. Every time when the land surface moves, it is because of that heat energy. So slowly and steadily the earth is losing that heat energy. It is predicted that in the next 3 to 4 billion years the inner portion would have cooled down quite significantly. Is that understood? right? If it is just a matter of collision of planetesimal objects, then how does Earth started to rotate? Again, I would repeat, if you have an object like this which undergoes a collision, it would have some rotation. Again, another collision, it would have some other rotation, and it would continue to move in that way. So it is by that multiple collisions and inertia that the actual movement, that the rotation happens. End of the star is the black hole. Okay. Prabjot, how is it that magnetic forces act as an indirect source? Because when you think about it, why does the planet Earth extend or subtend a magnetic force? That in itself gives you an idea about what that material would be present in the interior. After all, it is the source of information for the interior. How do we know that iron and nickel is present in the interior? How do we know that someone is not lying to us in the interior? Rather than iron and nickel, you have nothing. You simply have gold there, and nobody wants you to know. You do know that because of the magnetic field which is subtended. So magnetic field of the planet Earth helps you understand what is present in the region of the core. Okay. Asteroid don't have gravity. Who told you? Naina, why only collision took place? Why not fragmentation? Collision will lead to fragmentation also. But if you have two objects, let's suppose, who are moving against each other, that collision will lead to fragmentation. That happened in the case of Thea. But when you have an object moving like this, another object comes with a larger object, comes with a force, and basically subsumes that, there will be heat produced, but it will not get fragmented. Right? That is a portion of momentum, conservation of momentum, and the impact of it. Uh, that is the portion of physics I don't want to get into. Will on rotation of Earth, does Earth will rotate outside of its orbit? No. Is there a chance that Earth will stop rotating? No. Why not? It rains in the sun. What is required for rain? Water. Water is required for rainfall. In sun, what is it that you have? What do you think the sun is made up of? Girish, what do you think the sun is made up of? What gases? Hydrogen? Hydrogen combines to form helium. Can hydrogen form rain? No, you need water vapor. So that is why. Why we call Earth is tilted, as we know a circular material has no tilt or no cone. Because when we talk about the planet Earth which rotates, planet Earth which rotates, it is rotating like this. We know that. That is why we say it is tilted. Few of the planets, they basically rotate like this. Or a few of the planets even rotate like this. That is how we know that this must be the axis, this must be the axis. That is how we know it, that it is tilted. Okay, can we move ahead? During the Big Bang, from where did that singular particle? So, Big Bang theory assumes that there was that singular particle. It does not talk about the origin of the singular particle. That is where the oscillating theory of the origin of universe comes into existence. And I would tell you that, but not at the risk of confusing you guys out of your comfort zone. Basically, the oscillating theory, which is supported by the many of the physicists, is the fact that every few years, in the terms of every few multiple billions of years, the universe basically ends up, due to that Big Bang, it expands, it will move away, keep on moving away. Eventually, it will lose the energy. That is when the things, because they have lost their energy, they will be pulled by the gravitation of each other. They would start coming together. That is where they will again form that singularity. Again, there will be explosion. Again, it will lead to formation of the entire new universe. Again, everything will be condensed into the smaller part. If the moon was not formed, what is the effect of gravity in Earth? It would have been more powerful. Okay, is that taken care of? Any of you who have that urgent doubt without which life becomes difficult? Any of us having that urgent kind of a doubt? How the cooling happens after volcanic eruption? It gets into the contact with the colder atmosphere, the outer surface. Even now, when the volcanic eruption happens, the molten materials, do they remain molten all the time? They cool down. Why? Because in the interior there is heat, on the outside it is colder. So 800 degrees Celsius, 1000 degrees Celsius materials, when they come out, they get in contact with the 40 degrees Celsius air. It will cool down, it will solidify. Who first propounded the theory of Big Bang theory? Lemaitre and Gamow. Is optional geography similar with prelim syllabus? The syllabus is going to consist of these portions, but then optional, you have to study things in much greater detail. Where can I find geography current affairs? I'm not finding it in Hindu. If they're in what section? It will come. So, for example, a cyclone has occurred. That is a part of the current affairs of geography. That why a cyclone happens, if an earthquake happens, why it happens, if a landslide happens, where it happens. All those portions are the portions of current affairs. Okay. Are we comfortable now? Can we take a breather now? Okay. No, we can't. Since there was vacuum in the earlier time, how did crust cool down? As the number of collisions happened, as the number of collisions reduced, you had lesser number of collisions. So there was nothing which could produce heat anymore. So that is why the surface would lose heat to the outside space, outer space. And that is when the surface started cooling down. Okay. Why the stars are always hot as outer space is around minus 200, because the stars, they continue to produce heat due to the process of nuclear fusion. Sun is a star. Sun continues to produce heat because of consumption of hydrogen into helium, and then hydrogen gets converted into helium. So that process continues to happen. It continues to produce heat. Okay. Seismic waves are the waves generated during an earthquake. Okay. Now we come to, now any of the remaining questions that you have, take a glass of water, sip it in. After some time, even that will be cleared off. Now we talk about the aspect of the interior of the earth, or the structure of planet earth. So when we talk about the structure of planet earth, it is largely divided into three major layers. The thinnest layer, the thinnest and the lightest layer. Listen to this very carefully now. And let's put a hold to those questions now. 25 minutes I have addressed the questions. Let's put a hold to those questions. So the earth basically is divided into various different layers. The thinnest outermost layer, which is also the lightest layer, the layer that we live in, that is actually the lightest layer of the planet earth. That is what is known as crust. Crust is brittle. Brittle means it breaks easily. It does not get stretched enough. If it experiences some amount of forces, it can break easily. So crust, because it is the coldest portion, it breaks easily. I hope we are aware that when materials, they get very cold, they break easily, right? Otherwise you can stretch them, etc. For example, rubber. Take the case of rubber. Under its natural condition, if you stretch it, it can get stretched. But a frozen condition of rubber, it will break easily. That is the condition of crust. It is not frozen, but it is the coldest portion. It is the thinnest layer. So that is why it breaks very easily. It is brittle. That is why volcanic eruptions do happen. That is why when the internal forces, they try to exert forces in different parts of the planet, their surface simply gives way, it breaks, leads to earthquakes, etc. Then you have the portion in the interior of the crust, which is the bulkiest portion. That is what is known as the mantle. It is solid. Mantle is solid and it is very, very thick, but it is heated solid, so it can be deformed, stretched, etc. Its temperature is higher as compared to the region of the crust. Then comes the innermost portion, which is the core. So here you will find the outer core is in a molten state. Core has got two parts. Outer core is in a molten state. So here we find a trend that as you start going into the depth of the planet Earth, the temperature tends to increase. That is what is referred to as geothermal gradient. So as you move into the interior, the temperature increases. That is geothermal gradient. Temperature increases with depth. Okay. Now, so by the time that you reach the region of the outer core, the temperature is quite high. That is why the materials exist in a molten state. But inside that region of molten outer core, you have a very hot solid, that is the inner core. Inner core, as you can see here, is in a solid state. This portion is in a solid state. Why is that? Despite the higher temperature, inner core is in a solid state. Now, before all of you frame the same question, listen to this carefully. You will be able to understand this. So the inner core is in a solid state, but the outer core is in a molten state. Both of them experience very high amount of temperature. Yes, majority of you are correct here. The reason behind this is simple. That is pressure. For example, if you consider a solid, if you consider a solid object, okay, now if you heat it up, it will get converted into liquid. So it will get converted into, so in the case of solid, the molecules, they are attached to each other, closely bound to each other, isn't it? But if the solid gets converted or were to be converted into a liquid state, the molecules basically, they move away from each other. So we can say that liquid is basically an expanded form of solid. In order for a solid to get converted into a liquid state, it needs to stretch, it needs to expand, it needs to increase in volume, isn't it? But what if this solid has got enough pressure applied from all the sides that it has got no space to expand, no space to increase its volume, let's suppose. In that case, what will happen? If it has got no space to expand, regardless of how much you increase the temperature, what will be the case? It will continue to heat up, but it has got no space to expand. And expansion is needed. That is when the molecules, they will be able to stretch away from each other. So that is where it will continue to remain in solid. So in the region of inner core, the pressure from the surrounding areas is so high that it has got no place to expand. That is why it continues to stay in the solid state. Now, again, a follow-up question will be, But what about the outer core? Outer core is also present in the same area. Why that differential treatment? Why outer core is in liquid? Because even outer core has got a thickness of more than thousands of kilometers. So when we talk about the extent of the outer core has got a, it starts above the region of outer core, you have the surface of 3000 kilometers. But again, after that, you have substantial distance. So outer core has still got some area to expand. But by the time that you reach the innermost, you don't have any space to expand. Okay, that is why. Then another question which generally is followed here, but you have said outer core is liquid. Can't the liquid make some space for the poor inner core? In that liquid, can't they readjust ever so slightly so that the inner core can expand and convert into liquid? No, because the liquid of the outer core is also significantly dense. That is why it does not provide any space for the inner core to expand. So inner core is in a solid state because of very high amount of pressure exerted from all sides, and hence no space for expansion. Okay, so that is why the inner core continues to remain in the solid state. Crust is a thinnermost, mantle is quite thick, and then comes the region of the core. So that is the structure of the interior. So this is the structure of the interior when analyzed. Here, if you will observe, the radius is close to around 6,370 kilometers. Now, again, let me specify, crust and mantle is in a solid state. Crust and mantle is in a solid state. Outer core is in a molten state. Inner core is again in a solid state. Okay. Now, when we talk about the region of the crust has got a thickness of 20 to 50 kilometers. In certain areas such as the Himalayas, the crust has thickened even to the extent of around 70 kilometers, but that's it. Underneath the oceans, the crust is around 20 kilometers deep, and then begins the portion of mantle. Okay, so crust is around 20 to 30 kilometers, sometimes even around 40, 50 kilometers. That is your solid crust. Then begins the solid portion of mantle. Okay, immediately below the crust begins the solid portion of mantle. However, in the region of mantle, you have at a depth of close to around 160 to 200, sometimes even 400 kilometers depth, you have a layer where the materials, they do exist in a semi-molten, semi-solid state. Above it, in the portion of mantle, you have the solid mantle. Below it, again, the mantle is solid. It is just in this layer that you consider the portion is having semi-solid, semi-molten materials. I will come to why that is the case. But you can say that above it, you have the portion of solid upper mantle, above it, the solid crust. This portion of the weaker semi-molten semi-solid is also considered to be a part of upper mantle itself, because mantle, which starts extending right from a depth of 50 kilometers, extends all the way to around 3000 kilometers in depth. That is the entire extent of the mantle. So even this particular layer, which has got the semi-molten, semi-solid substances, that is known as asthenosphere. So even that asthenosphere is considered to be a part of upper mantle itself. Okay, but if you go into the specific, above asthenosphere also you have the portion of solid mantle. So this is the portion which is known as asthenosphere. It is derived from the term asthenos, which basically means weak. Asthenosphere. Here you have the solid crust plus solid upper mantle both of them together. That is what composes lithosphere. So when we talk about lithosphere, lithosphere basically consists of the portion of the solid crust along with the solid upper mantle that is included in the portion of lithosphere. Underneath that lithosphere, you have a weaker region where you have semi-molten, semi-solid materials, that is the asthenosphere. Now, when I say semi-solid and semi-molten, I'm not saying molten, neither am I saying solid. So, what is that conundrum? So, it is not completely solid, not completely liquid. For example, if you take the case of molten glass, it does not flow like a liquid, does it? Molten plastic, it doesn't, it can get stretched, it can be in a molten state, but it does not move like a liquid. Neither can you classify it as a complete solid, can you? So that is the condition of asthenosphere. Asthenosphere is in a semi-solid, semi-molten state. Now, why is that the case? That is because at these depths, you find the sudden dominance of certain radioactive elements. Radioactive materials such as uranium and potassium, they are dominant at these depths. Okay. And owing to the geothermal gradient, that basically means that as you start going into the depth, the temperature is increasing. At these depths, the temperature is also high. The pressure exerted from above is also high. So that is where these radioactive elements, they undergo a thermonuclear reaction. And as a consequence of that thermonuclear reaction, they produce so much heat that all the materials around it, they are partially converted into semi-molten, semi-solid state. Okay, so here at this depth, so don't think about it that, so that means all the uranium is found there and we have been searching for uranium in Australia, Kazakhstan, Canada, etc., but you are saying uranium is present in asthenosphere. No, the surface uranium that we talk about, the mineral extraction that we talk about, that is different. This is at a depth of more than around 160 to 200 kilometers, so significant amount of depth. Okay, so at this depth, you have the dominance of radioactive elements like uranium and potassium. Now, it is not plutonium, it is potassium, the isotopes of potassium. Under high heat and pressure, they undergo radioactive or thermonuclear reaction, produces high amount of heat, very high amount of heat, and due to that heat, materials around it, materials partially melt under very high heat. That is why at that region of asthenosphere, you have the semi-solid, semi-molten state. So asthenosphere is also considered to be a part of the upper mantle. But lithosphere, when we say lithosphere, lithosphere consists of the solid portion. Why both of them are upper mantle? Because a mantle whose thickness can stretch for 3,000 kilometers or so, there 200 kilometers or 150 kilometers, they don't make that much of a difference. So above it also mantle is solid, below it also mantle is solid, below it also it is solid, right? So it is only in that layer of asthenosphere where you will find the material to be in a semi-molten, semi-solid state. It is in fact this asthenosphere which is the supplier of all the molten materials that erupt on the surface in the form of volcanic eruptions. All of them, they come from the region of asthenosphere itself. Okay, now let us take a look at the written portion of it. So crust is the outermost solid part of the earth. It is brittle in nature, means breaks easily because it is very cold. As compared to the inner portion, it is the coldest portion. Now here, the crust is made up of various different types of materials. Okay. Now, and its thickness also varies. For example, in the continental areas, its thickness, basically mean average thickness, is around 30 kilometers from the surface. In the region of oceans, its mean thickness is around 5 to 20 kilometers. That's it. Right. So underneath the oceans, the crust is what is known as the oceanic crust. Oceanic crust is thin. Continental crust is thick. But they are made up of different materials. That is why they have different densities and different weight. Continental crust, regardless of its thickness, is always going to be lighter, very light. Oceanic crust is always going to be very heavy. Continental crust is dominated. When we say continental crust, it is dominated by materials such as granitic rocks. It is dominated by granitic rocks. So elements such as silica and aluminium. Silica and aluminium dominate that. And when we talk about oceanic crust, it is said to be dominated by the basaltic rocks, which have iron content, magnesium, etc. High density. I hope we are aware about the term density. We have come across the term density earlier in our lives. Okay, we are not aware about density. Density is basically how closely the molecules are. What is the closeness of the molecules? So density is mass per unit volume. So in the same volume, what is the weight, right? Take, for example, thermocol and take the case of iron. Thermocol, you can have a large volume. It will be still very light. Iron, even if it is of a smaller volume, it will still be heavier, right? For example, if you talk about iron sheets, are and steel columns, they are very thin. Near it, take a very thick thermocol piece. Volume of thermocol will always be high. But which will be heavier? Iron or thermocol? Always iron. Always iron will be heavier. So why? Because in thermocol, materials are not closely packed. Iron materials are very closely packed, right? So basaltic rocks, they are made up of silica, magnesium, iron in dominant. Density means dravyaman, ghanatva. Yes. So all those of you who can basically take that into consideration, that is also the meaning of density. Ghanatva is something that I was aware of. Dravyaman is a new translation that I came across. Thank you for that. So basically, basaltic rock is dominated by silica and magnesium. Hence, it is more dense. Density is higher. Always, oceanic crust is going to be heavier as compared to continental crust. Always, regardless of the thickness. Of the thickness. Oceanic crust is heavier as compared to continental crust. Okay? Always, oceanic crust is going to be much heavier as compared to the continental crust. So the continental crust is thicker in areas of major mountain systems, in the regions such as Himalayas, where there is a crustal compression which happens. The crust can be as thick as around 70 kilometers. Right. So the continental crust, composed chiefly of granite, has a density of around 2.7 gram per centimeter cube. And the type of rocks found in oceanic crust is basalt, where the mean density is around 3 gram per centimeter cube. So that is why basically you will find that significant amount of weight is associated with oceanic crust. This is going to be always going to be heavier. Then after the region of the crust, which is the thinnermost portion, that is where you come across the region of mantle. Mantle is very thick and it is also dense. Density, by the time that you reach the lower regions of mantle, the density is very high. So average mean density in the portion of mantle is close to around 3.4 gram per centimeter cube. Mantle starts in extension or starts in existence right underneath the portion of the crust, and it can extend up to a depth of around 2990 kilometers or up till around 3000 kilometers. You will find the depth of the mantle, so that is significantly thick. Now it represents around 68% of the earth's mass is represented by the region of mantle itself. That is how voluminous it is. Okay. However, in the portion of the mantle, in the upper portion of the mantle, you have the asthenosphere. Now, asthenosphere is derived from the term astheno, which means weak. It is considered to be extending up to a depth of 400 kilometers from the surface, and it is the main source of magma, the molten material, which finds its way to the surface during major volcanic eruptions. Then we come to the region of the core. Now, core is the innermost layer of the planet Earth. It is dominated by iron and nickel. The temperature is so very high that the outer core is in a molten state, but the pressure is so very high that the inner core, despite the high temperature, continues to remain in a solid state. So when we talk about the region of the core, because of the dominance of iron and nickel, that is why it is also what is known as the Nephi layer. Okay, Ni stands for nickel, Fe stands for iron. So The core mantle boundary is positioned at a depth of around 2900 kilometer. The core makes up around 31% of Earth. Inner core is in a solid state, whereas the outer core is in a liquid state. Okay, it is made out of heavier materials. Now, if I talk about the basic question, while writing the notes, is it important to draw the diagram in the notebook? It depends on you. If you can retain that diagram, you can basically reproduce it in the examination, fair enough. So basically, I want you to apply logic here. When we talk about a region in the crust itself, let's zoom in the crust. Now, if I ask you the pressure exerted by the rocks here, let's name it as A, and the pressure which is experienced by the rocks here at B, where do you think the pressure will be higher, A or B? How in A the pressure will be higher? What is the logic that you have provided for A, the pressure being higher? Or is it simply because that he was saying A or B, I had 50-50% option, so I chose A? So kindly could you elaborate, few of you? Why do you think that pressure will be higher at A? No. Now converting your answer to B doesn't work. If you have written A, okay, atmosphere. Okay. Okay. Basically, the pressure will be high at B because here you have only few, maybe 1 kilometer of rock above it. So that is going to extend the pressure. Here you will have many kilometers of rocks above it. That is going to extend the pressure. So as you go into the depth, the pressure increases, the temperature increases. Due to the increase in pressure, due to the increase in temperature with depth, eventually you will find that the molecules, their pattern changes. The type of materials, they start to change. You have different arrangement of particles, different chemical properties exhibited and indicated by the particles. So as you start moving into the depth, in the crust, in the portion of the mantle, you will find that the nature of materials, the nature of the rocks, all of them, they undergo a kind of a change. So there is that zone of transition from where different kinds of materials will start dominating. And that zone of transition, that is what we refer to as discontinuities. So, for example, in from the region of the crust to the region of the mantle, as you go from crust to mantle, the nature of materials, the nature of rocks, they will change. As you move from mantle to the region of the core, the nature of materials, the state of materials, everything will change. So that transition is known as discontinuities. So basically, planet Earth has got various different discontinuities in the interior. Now, this is going to be relevant. The name and where it is present that match the following kind of question can be asked in from this particular portion, particularly in your prelims examination. So here, when we talk about the region of the crust, you have a discontinuity which distinguishes the outer crust from the upper crust from the region of lower crust. And that is what is referred to as the Conrad discontinuity, which basically differentiates the nature of the rocks that you find closer to the surface. But as you go to the depth of the crust, the material arrangement, etc., changes. Then, between the crust and the mantle, that boundary between the crust and the mantle, there also you will have the different types of materials which are present. That is what is known as Mohorovičić discontinuity, okay, or what is simply referred to as the Moho discontinuity. In geological terms, it is sometimes simply referred to as the Moho. For example, when an earthquake occurs, you will hear in the, or if you read the detailed analysis of it, if ever, you'll find it mentioned there that the origin of the earthquake was 12 kilometers from Moho, was 15 kilometers below Moho, was closer to Moho. So Moho basically stands for Mohorovičić discontinuity, and that is the discontinuity which differentiates the region of the crust from the region of the mantle. So Mohorovičić discontinuity differentiates between the upper, or between the region of the mantle and the region of the crust. Then in the mantle also, you have the upper mantle and the lower mantle. They are also separated by a discontinuity. And that is what is Repeti discontinuity. All of them are named after the individuals who basically found that. Then after that, the outer core is molten, the portion of the lower mantle is solid. So there also you will have a discontinuity, and that is your Gutenberg discontinuity. Then the outer core is liquid, inner core is solid. So there will be a demarcating layer, or that zone of transition between the liquid outer core and the solid inner core. That is what is known as Lehman discontinuity. So these are the various different discontinuities which basically demarcate the different types of materials, or the variation of materials as you move from the surface to the depth. Okay, these are the various discontinuities. So discontinuities simply tell us that, for example, the surface of the crust, different types of rocks. If you go to the depth of 50 kilometers, you will have different types of rocks. You will have different pressure exerted, so the molecular arrangement will be different. The pattern will be different. The chemical properties will be different. So there will be that zone of transition which will be created in between. That is the discontinuity. So discontinuities, they get created due to overlying pressure, temperature, nature of materials. For example, mantle and core. Mantle is solid, core is liquid. So there will be a region where above it you will have solid particles, beneath it you will have molten portions. So that is the case of discontinuity again. So this is the portion or the reality of the discontinuity. For your prelims, you can have the match the following. That Conrad, which it is between upper and the lower crust, Moho between the crust and the mantle. This kind of a match the following question can easily be asked in the prelims. For your general studies, it will be sufficient if you are aware about what is Moho between the crust and the mantle, and what is Gutenberg, right, between the solid mantle and the molten core. So these discontinuities, you take care of it, your portion of GS prelims is taken care of in this area. Now after this, we come to the minerals. Basically the minerals which are present in the interior of the earth. Here also questions have been asked previously about which minerals are dominant in the interior of the planet. So when we consider Earth as a whole, inclusive of the surface, the interior, everything, iron is the most dominant element, followed by oxygen, followed by silicon, magnesium, and so on. Now here, oxygen. How is it that oxygen is present in the interior? What do you think? How is it that oxygen is present in the interior here? Are we able to think about it? Yes. Amritansh, good. Godavari, good. This oxygen, when we talk about, it is present in the form Debanjan, very good. Anant Krishnan, good. This oxygen is present in the form of oxides, the solid form, right? You will find iron oxide, silicon oxide, etc. So that is where this oxygen is present in the oxide form, okay? Present in the form of oxides, solid form, in the form of oxides. Example, silica, ferrous oxide, alumina, etc. If you consider only the Earth's crust, there oxygen is the most dominant, followed by silicon, aluminium, and iron. For your examination, this is the portion relevant for your prelims. For your examination, only the top four need to be studied. Only the top four need to be covered for your examination here. Now, this oxygen also is in the form of oxides. It is not the gaseous oxygen that we are talking about. We are talking about the surface and the interior. So here also we are going to talk about the oxides only. So here also the top four, that is something that you should ideally keep in mind. Okay. Now, then we come to the portion of rocks. So when we talk about rocks here, but before that, let us talk about something different. Let us talk about geomagnetism. That is magnetic field. Extended by Earth. Now, when we talk about planet Earth, we know about the structure now. I hope we know about the structure now. Now, when we have seen the structure, we have also seen that in the region of the core, you basically have the molten outer core, and then you have the case of solid inner core. Molten outer core, solid inner core. Okay, before that, I don't know how many of you are from science background. I'm assuming that none of us are from science background. So in that case, I hope we are aware of a phenomena that if you have a kind of an electricity which passes through that circular spiral, let's suppose you have a circular wiring like this. Are we aware about electromagnetism? Have we heard about the term electromagnetism? Right? Where magnetic field is subtended with the help of electricity? Yes? Now, yes, this is a solenoid, but again, so as the electric current passes through here, electric current as it passes through here, this basically subtends a magnetic field like this. Okay, so passage of electric current in a spiral extends electric or a magnetic field. Were we aware about this? No? You would have heard about the maglev trains in China, right? Where are you going into Faraday's law, etc.? That is like too much into science. I am going to bring it down. Ashish, I hope you are aware about it that many of um, the candidates, they are not from science background. So if I use Faraday coil, etc., that will create a panic which will be unparalleled. So you would have heard about the maglev trains in China. Maglev trains basically is I hope you are aware that in China you have the train system which can move at a speed of around even 500 kilometer per hour, 600 kilometer per hour, and that works on the property of magnetic field, where the train simply doesn't move on rails, it floats on the railway track. It kind of floats because of the magnetic field. It does not touch the rail, it simply tends to float on one on the other, and that is why it is able to gain a speed of around 550 600 kilometers per hour, right? That works on this principle of electromagnetism. Is with the help of electric current you are able to produce a magnetic field associated. Even if we don't know it, are we able to digest this reality of life? I understand that yesterday many of us were unable to digest that reality, that how come poles are in darkness. Nobody told me till now. So are we able to digest this reality? Fair enough? Okay. Now, if that is the case, so here, now let us talk about the Earth. Earth is consistently rotating on its axis from west to east. In a direction west to east, Earth is consistently rotating on its axis. So, as the planet is consistently rotating on its axis, you have the molten outer core, which is in liquid state, means very high temperature, right? Molten state, very high temperature. So, that means that molten outer core, liquid is also moving in a kind of a circular motion. Because of that very high temperature, that particles of iron, nickel, etc., they have electrons which escape the molecule, or the electrons which escape the atom. So you have presence of movement of electrons and ions. Charged particles, they start moving in the region of charged particles. Basically mean, if let's suppose in an atom an electron escapes, it is a charged particle, right? So as at that very high temperature, molten iron and nickel, they continue to rotate in a circular motion. You will have the electrons which also start moving. So the charged particles, they continue to rotate in a kind of a circular motion. And when they rotate in a circular motion, it will be like passage of electricity like this, because electrical current is also about the movement of electrons. So that is when it will be like the movement of the charged particles all around it. And that will subtend a magnetic field. That will basically subtend a kind of a magnetic field. So this magnetic field, which is basically subtended, that is what is referred to as geomagnetism. So that geomagnetism is extended because the planet does rotate and because the outer core does rotate. So the outer core rotates in circular motion due to high temperature, charged particles of iron and nickel move in circular motion. It extends a magnetic field, that is geomagnetism. That is what we refer to as geomagnetism. Okay, so that is the case of geomagnetism, because as the outer core also rotates, planet rotates, outer core is in a liquid state, so the outer core will also rotate. Outer core consists in the core consists of what? Iron and nickel. So at high temperature, it can happen that one electron of an atom will escape. So as it rotates the outer core, we can also think about it that the electrons or charged particles are rotating in a circular motion. Whenever they are rotating in a circular motion, they will be subtending a magnetic field. That is geomagnetism. Now, for your general studies, even if you know that Earth subtends a geomagnetism, more than sufficient. Nobody is going to ask you the detail about it. Okay, even if you know that planet Earth, because of the movement of the rotation of the outer core, it produces a magnetic field, more than sufficient. Now, here, when we talk about, for example, if you talk about the compass, right, the compass readings that you get, compass always points to the north. Now that compass, why does it point to the north? It is based on the magnetic field of the planet Earth, right? Now here, if I elevate this level of concept, I hope you are okay with this particular level of concept. No, this is different from the force of gravitation. Force of gravitation is the force of attraction. Magnetism is different. Iron magnets, they, you would have seen fridge magnet. Fridge magnet, basically, if you see it, that is magnetism. If that magnetism is induced because of movement of charge, that is electromagnetism. Okay, now here, when we talk about the region of outer core, it consists of iron, nickel in a molten state. But will that be in the same molten state like you think of water? Or do you think it will be slightly viscous like honey, for example? Just as a point of reference, I'm giving you. Don't quote me that outer core is consisting of honey because it was told in the class. No, I'm just telling you about it. That iron and nickel in a molten state, will that be in a state of fluidity like water, or will that be viscous like honey? Slightly viscous, isn't it? It will slightly be viscous. So it doesn't flow very easily. So it can happen that outer core sometimes will have a chunk of iron and nickel, let's suppose developing somewhere, a large bulk of it developing somewhere, concentrating somewhere. That is where the rotation is happening. Let's suppose from here that chunk has traveled all the way till here. Now that will impact the magnetic field. That will mean that the magnetic field now starts extending from here. So that is why, because the outer core, excuse me, because the region of the outer core consists of these materials, and these materials, they can simply end up moving from one region to another in bulk, in large bulk, in large quantums. That can have a potential to impact the magnetic field. And that is why the magnetic poles of the earth, they are prone to shift. Magnetic poles of earth, they are not fixed in the same place. They are prone to shift. You might have sometimes a magnetic pole coming here, sometimes a magnetic pole coming here. In 2020, for example, the magnetic north pole of planet earth, that shifted from the region underneath the area of Siberia to the region underneath Alaska. Because in the region of the core, you had that massive shift from the region of the bulk of iron and nickel moved from one area to another. Now, the magnetic poles of planet Earth poles of Earth are prone to shift from one region to another and can also revert in polarity. That is the concept of geomagnetism. So, if I ask you a question, ever since the formation of planet Earth, the magnetic field of planet Earth or the magnetic poles of planet Earth have changed multiple times. True or false? What do you think? True? Very good. This was the question which was asked again in 2018 prelims. So, if you can think about it, you can get those questions correct as well. So, that is the concept of geomagnetism. Okay. Now, this geomagnetism basically has got its influence in the form of the northern and the southern lights. So, when we talk about magnetism, so we do know that planet Earth subtends a magnetic field. Now, the properties of the sun, which you study in the portion of science and tech, sun time and time again discharges heavy amount of charged particles into the solar system in the form of solar winds and solar flares. The sun ends up discharging very large amount of charged particles. Okay, in the form of solar winds. Now these charged particles, they are emanated in the form of solar flares and solar winds, which end up moving at a speed of thousands of kilometers per hour, and they end up reaching the region close to the planet Earth. But as they approach the planet Earth, these charged particles, they are influenced by this magnetic field lines, and that is when they will always go to the area where the magnetic field lines have the greatest density. And which is the area where the magnetic field lines have the greatest density? Around these regions, higher latitudes. This is where magnetic field lines will have the highest density. So that is when these charged particles, they end up traveling like this. They go for an angular shift. In fact, the Aditya L1 mission, which we have sent, one of the prime purposes of that Aditya L1 mission is to study that angular shift, is to basically work upon and understand how that angular shift happens. So basically, that is how that shift does take place. Now, here, you will find that as they reach these region closer to the poles or the higher latitudes, these charged particles, they interact with oxygen molecules, nitrogen molecules, which are present in the upper atmosphere. And that interaction with oxygen and nitrogen, that produces very unique and picturesque hues of light. That is what we refer to as auroras. In the region of the northern hemisphere, closer to the poles, that is in the region of Norway, Sweden, Finland, Greenland, northern Canada, Siberia, and also the region of the Arctic. That is what is referred to as northern lights. Every year, thousands of tourists they do visit these areas to witness the northern lights. So auroras, you have northern lights, or what is also known as aurora borealis. And in the southern hemisphere, they are known as southern lights. People do visit New Zealand and Australia every year to witness these southern lights, where the sky basically is painted green, blue, and various different hues of color. It is like a river of light which flows into the night sky. So, this is also what is known as aurora australis. So, that is basically the magnetic field which does impact the charged particles emanated from the sun, and that is why these areas they experience this. Okay, so that is the situation or the condition why we experience northern and the southern lights. This is where we'll limit the discussion here for today. I want you to digest this, revise this. Tomorrow we will continue from the portion of the area of rocks. Auroras basically are produced when the charged particles of the sun they get emanated from the sun on a very regular basis. And whenever they get emanated from the sun, that is when they will come towards all the planets. And when they approach the region of the earth, they will basically aid, uh, aided and impacted by the magnetic field. They basically get directed towards the region where the magnetic field lines are of greatest density, and that is when they will come to the polar areas. Okay, so that is the case of why when they interact with the oxygen and nitrogen molecules at our upper atmosphere, they end up emanating light. Okay, Shiva, find it on YouTube. You will find the uh, IDL, search it on Byju's exam prep, you will find that. So this is where we'll restrict the discussion here today. You have the webinar sessions also. And Seema, if the outer core has iron in the whole section, then why magnetic pole shift? Because in certain areas you have a greater density. In certain areas you have less density. So as that greater density region shifts, the magnetic pole also shifts. In lithosphere, which is the outermost crust or uppermost mantle, the crust plus the uppermost solid portion of mantle taken together, Sushmit, that is lithosphere. Why can't rotation of solid mantle and inner core? Because you need the movement of the charged particles in a circular manner to extend that magnetic field. Okay, then why magnetic field felt in pole only, not all over the earth's surface? Because it rotates in this manner. So as it rotates in this manner, the magnetic field will be perpendicular to it. Yes, Rumaiza, I answered your question earlier also that while writing the notes, is it important to draw the diagram? Whatever is required for you to recollect the diagram, that is sufficient. Groundwater is present in the upper portion of the crust itself. So that is where we restrict the session here. We meet again tomorrow. Take care of yourself. Goodbye. Attend the webinar sessions and we will continue tomorrow. Thank you. Goodbye. Have a good night.